So, ladies and gentlemen, good morning, everyone. It's almost the last lecture of this course. We are closing to the end. Only homework has left. And today there is a second lecture on dissipative quantum mechanics. What was there? In the previous lecture, we've been looking at oscillator in the presence of dissipation. We understood the difficulties, we solved them. Well, what we understood actually, that oscillator with friction is a infinite set of oscillators, right? Because one has to involve many degrees of freedom to describe dissipation. Well, it was a nice message, but it's boring. Just yet another set of non-interacting oscillators we've been looking at. We are up to challenge. We look at more interesting results of dissipative quantum mechanics, and they, in German framework, refer to transitions with presence. To start with, I spent quite some time to go from an oscillator to more complicated, interesting system and introduce the notion of transition in the system. It would be like a qubit, right? We will understand what would be equivalent model, which is, okay, it's again notations, which is called Spin-boson model. It's not about spin, it's not about bosons, but it's called Spin-boson. Right. Spin-boson model is a complex one, but we can successfully treat it with perturbations. And there, our knowledge of coherent states, and the whole lecture on that coherent state, that will be very useful. And we'll be able to crack this problem, at least in perturbation limit. The results are astonishing. We will learn about orthogonality catastrophe. Again, it has something to do with orthogonality. Whether it's catastrophic or not, it's up to you to decide, but that's kind of right. And we go to the details, and we will understand that environment can qualitatively modify the properties of transitions. Say, an example I would mostly concentrate on would be an example of qubit, which can be made classical member cell by choosing proper environment, proper interaction and dissipation in post-process transition. Right, that brings us to the classification of environments which have been put by Tony Leggett, like 35 years ago, something like that, right? That will give us an overview of the topic. And finally, we will look at our work at vacuum, physical vacuum, and field of radiation, and we will understand what is anomalous about our work. Fine, that's the plan for today. Let me go step by step. First, to remind the oscillator that is at classical level a particle in potential relief, so there is a force which tries to bring it to the center. There's external force to drive the particles. There's friction force, which requires so much of modification when we treat it quantum mechanically. Right, so how we can make something interesting out of that? How we can complicate oscillator in such a way that something interesting would come about. Good. One could change a bit potential profile, say add cubic term, whatever, change it from parabolic to something else. Wow, that would hardly bring a quantitative change. What would be quantitative change? That potential has a single minimum. If I make it 2, that will be quantitative change. So I will modify this potential. So it becomes like this. Also, well, if it contains, if it has 2 wells of different height, then I have an idea that the system is in the lowest well anyhow for all interesting situations. So I would better align these wells. Okay? Right. Can I describe the system? Yes, I do. I can. Well, I would have the same equations of motion in classics, right? I would only have a different potential. That's a red term in equation for by dot. I would know how to write friction force in classics, but I will have no difficulty to quantize it as well. With all knowledge you'll have. The only point it will be operator x, which will be the corresponding term won't be linear on x. We'll have some more complex terms. Equations won't be solvable anymore. It's getting boring. Perhaps it's too complex of a system. So let me now to extract the essence from the model. How would I do this? I would do it as follows. Let me forget about the friction, about connection to environment, to the bus. Let me just understand it in terms of normal quantum mechanics. If I align 2 wells, the lowest state in each well will be delocalized. I will talk about delocalization several times. You know this phenomenon, perhaps you cannot relate delocalization to this. Let me make sure that you understand each other. So, if 2 wells are aligned, there is also some channeling amplitude between the wells. The states here and here, they overlap a bit. That's why we have hybridization of these 2 states. If the wells are aligned ideally, it will be just odd and even superposition of these 2 states. They will split in energy corresponding to 2 states of the qubit which are completely delocalized. They don't know what is right, what is left. they come there with equal chances. Good, that's quantum mechanics. Let me just go a little bit forward, but simple, I will explain. So all the lecture will explain how to go between these two pictures of the slide. So let me just give the limit right away. The limit, then we will come, let's turn dissipation. It's the limit of classical qubit theory. If I get quantum mechanics, we have a particle which is either on the left or on the right, no delocalization whatsoever, and in fact no levels, because of the classical particle with friction won't have any excited states. Right, so those are two limits, and let us try to understand how we can go between these two. So let me concentrate more a bit. This is the starting point. It's because your last lecture, that's what it tells you about two-level system or qubit or spin, whatever you call it. So please be attentive. My qubit is realized as two wells with tunneling amplitude delta between two wells. And epsilon is energy disalignment of two levels. Fine. But as any qubit is no regard for physical realization, I can describe by a 2 by 2 Hamiltonian by 2 by 2 matrix, which is made as any 2 by 2 matrix from Pauli matrices. Good, so what would be in our case? I'm working in the basis of left and right state. So this epsilon comes on diagonal. So one level, difference of height between two levels. The delta comes as sigma x, and it will mix states on the left and on the right. If epsilon is 0, then we have these odd and even superpositions. All right. All of you can diagonalize this Hamiltonian, or eventually, if you're not through homework yet, right? So who did homework 8? Okay, there's still several days to do this. Okay, basically what is here on the slide is a path of homework 8, when we need to diagonalize qubit, and my unfortunate constatation that 99% of students can derive this formula without any difficulties, and only 9% can arrive to this one. So make sure that you belong to 9%. So, what's the difference? It's eigen energies of the Hamiltonian and its eigenfunctions. Let me concentrate on the quantity which I like, and I will call it delocalization probability. So I have a lower well, and I would like to find the probability for a particle ground state to be in an upper well. Okay, that will be 1/2 if the wells are aligned, if epsilon is 0. Okay, one can see it from this. But I'm more about large energy biases, large misalignments. Why is it so? Because it's convenient for me to treat delta as a perturbation. Okay? And in this limit, I still have some finite delocalization probability. It's small, it's fine, but still there is delocalization probability. It's small if epsilon is huge in comparison with delta, but it is finite. Good. That's what we want to recall about the qubit. Any questions? All right, I hope you recognize the qubits. So it could be spin in magnetic field, and those will be Z and X component of the field. That explains next thing. All right, that was a particle, about the particle in a potential. Could be an electron between the atoms, could be an atom between two lattice sites, many systems. But let me try seemingly completely different system, and let me show that the essence is still the same. Okay? What I want to do, first of all, I want to set up an electric circuit that contains a capacitor, inductor. Okay, that would be again another Born oscillator. I want to make something else, so I put a resistor to ensure that there's some dissipation going on. Fine, that's electric circuit. And now I'm gonna make a trick. I wanna get another element. I will allow for electron tunneling through the capacitor. Okay? So capacitor from electric circuit theory doesn't have any conduction, but physical capacitor consists of two leads separated by oxide layer, and electrons can tunnel through this oxide level. Okay, what would I have? I would like, I would see some states, electronic states on the left. Okay, it's not the left, it's on the bottom lead, some states on the upper lead, and there is some tunneling amplitude which contains each pair of states. Fine. If I look at the transitions, I understand that the fact that I have a huge number of states doesn't really matter. Yeah, because if I have a transition, I always transit between two states, two discrete states, on the top and on the upper. Fine. So quite strangely, these models have common ground, have common formulation. We just need two states which are coupled somehow to the environment. Fine. With this, I want to sketch the spin-boson model. What is spin here? No physical spin. Spin just says that there's a qubit involved. Good. So I bring my qubit. I want it to be coupled to a bath, which we have used in previous lecture to infinite set of harmonic oscillators. Here they are. Okay, that would be too simple to treat, so I want to couple. Suddenly, I want to couple the qubit and the states of the lines. I do it as follows. Sigma z. It shows if the qubit is on the left or on the right. You not. Add some coupling constant. Suppose I'm breaking this charge particle, it could be charge on this particle. And I would like to have some force which comes from the environment and consequently is expressed as a field operator in these bosonic fields. Right? So bosons come from the bus, spin comes from the qubit. Fine. So to write this first, I invoke the coefficients in principle, individual coefficients for each mode, which makes it complex and incomplete. How can I make sense of this? That force is coupled to this term. Let me call it charge. And that takes two positions in my system. Plus Q naught and minus Q naught. Do you understand why? Because it's sigma z matrix, it has eigenvalues plus and minus. Suppose I can make it a discrete value. For 2 wells potential, it's something which is easy to understand. It has, the qubit has 2 positions plus minus in the mouse, but I could also just grab it with my hand and move it between 2 wells. Good. This gives a response. It gives a friction force provided by environment. And this is precisely this force. So I can characterize it if I know dynamical susceptibility. Precisely as we did for M oscillation. So instead of the senseless C of M, I could use the formula which relates the square roots of these values at each energy to imaginary part of dynamical susceptibility. Good. That sets the spin-boson model, the ultimate model, to look at the transitions in the presence of good. In general, it's too difficult to solve. People, of course, look at numerical solutions, things like that. But basically, all results, all interesting results, can be done much simpler reasoning, can be done if you just consider this problem in perturbation limit. So we will assume that epsilon is huge in comparison with tunneling amplitude. Good. So now we are going to make our hands dirty and crack this problem. Okay, yeah, not yet. Our hands are not dirty yet. It's just illustration again for the same concept for electromagnetic environment. So what we have here is a coupling operator or a charge which goes from one plate of a capacitor to another plate. The energy associated with this charge is given like this. So just voltage which is across the capacitor. Okay, you move an electron either in the direction of voltage or in opposite direction. So you have the sigma z with two sides. Okay, and what would be the corresponding, so voltage will be at the separator F force, and how to compute dynamical susceptibility. It's a reaction of this voltage onto this charge, which I would move in the capacitor. But the charge is the same as a current source, right? So I can relate everything to the electric impedance characterizing the circuit. So I can make sense of this coefficient C of M, can express it in physical terms. Okay. Right, so let's make our hands dirty. It's a simple problem, but well, it requires some steps. Delta is zero. Delta is zero, what does it mean? We have two separate worlds. In one of the worlds, qubit is in upper position, in another world, which is absolutely dependent. It's in opposite position. No transitions between these worlds because delta is zero. All right. Let me write the Hamiltonian. It contains all modes of the bus, and it contains this extra term, which is linear in terms of creation and annihilation operators, and comes with plus minus two possible qubit positions. Good. So we want to diagonalize this Hamiltonian. Understand its whatever wave functions and energy levels. It's important for us to understand that these keys, this plus minus, shift the ground state of this oscillator. Well, plus minus means opposite directions. How to understand this? First of all, we have quadratic term and linear term. If I forget about all the separators, if I just write potential for a single oscillator, it is parabolic. I add linear term. What will I get, ladies and gentlemen? That's kind of still problem. We spin the day. Let us recall that the resulting potential will be parabolic potential gain is a shift with respect to original parabola. Okay? Remember that? Good. Let me get it in a bit formal fashion. Let me solve this Hamiltonian, introducing new creation-relation operators different for plus state and for minus state, which are obtained from our command creation-relation operators by shifts plus minus lambda. So how we proceed, we express B's in terms of B plus minuses substituted into the Hamiltonian and choose lambda in such a way that the Hamiltonian becomes like this, that the Hamiltonian does not have linear terms anymore. Again, it's similar what you did at school when looking at the shift of parabolic potential. Okay, this operator is something we know, right? And we understand that it has vacuum and excited states. That's, an oscillator. So for each position plus and minus, we have an oscillator. It's precisely the same frequencies. However, there is a difference between vacua of these two oscillators. These vacua are different. How to find the relation between those? Okay, that's kind of all logical. This is definition of the vacuum at position minus of the qubit. Now I substitute instead of B plus, instead of B minus, B plus. Annihilation operator, but in the plus position of the qubit. And this relation becomes like this. Okay, this is annihilation operator. Who can remind me when did we see this equation? Yes, precisely. This is the definition of coherent state. So this is for a wave function, which happens to be a vacuum in minus position. The conclusion is that the vacuum in minus position is a coherent state in the basis of bosons in plus position. Okay? That's the flashback of coherent state. It's an eigenfunction of annihilation operator. It can be nicely expressed analytically or given a number of bosons. Here it is. And one of the vacuums is a coherent state with respect to another one. What does it mean? It means that this vacuum, for instance, its minus position is a superposition of all possible photon states in plus position, and equals 0, 1, 2, 3, 4, and so on. Good. So let me go to shake up how to implement shake up of the oscillator in this context. Good. So look at the figure. We have an oscillator in minus position. It's in one state, it relaxes, it kind of slips a bit. We're not aware of what will come. What came is a transition. So the potential profile of the oscillator has changed quickly. Wave function, which has been sleeping and relaxing, of course, it didn't change. But now, look, it becomes a wave function of excited states. Okay? Was a vacuum in minus position, becomes a superposition of excited states in plus position. Right. That can be characterized by shake-up probabilities. Probability to find the system is energy E, positive energy E in new position. Good. We've been working with one oscillator, and in this case, this energy loss, energy gain, is quantized. According to equidistant levels of the oscillator. It is quantized. The probabilities are readily expressed in terms of coefficients of coherent states and appear to be given by Poisson distribution. This Poisson distribution has a single parameter, average number of photons, which is emitted during a shake-up. Here I sketch the distribution function for some n bar, which n bar it is. Please look at the figure, and give me an idea. What you see in red bars is a probability distribution. N bar, its average, how much it is. Don't tell me that you need to calculator to determine the average of this distribution. Tell me, how much is this? I would bet for 3. But yeah, it's accurate, sufficiently accurate estimation. So average is somewhere here. Fine, good. I am pleased to have kind of very complete correct formula for this shake-up. It looks kind of involved, but it's Poisson distribution, which comes in many, many different areas of physics related or unrelated with stochastic processes. So we have shaken up a single oscillator. Now a little bit an effort. What kind of an effort? We're gonna shake up many with a shape shift. So our qubit jumps from one position to another position, being coupled to plenty of oscillators, and eventually, if you just move it, you will shake up each oscillator. We are not interested in individual oscillators. What we want to know just probability to get energy E in course of the shake-up. Right, so what I did here, I just collected Poisson distributions for all modes. I have to sum up over X, and I have to sum up over Nm number of photons emitted in each mode. The energy which I get in this way, just write it as a dot function. It's okay. So it's a probability to get excited with energy E in the course of the we will talk about this. Let me first look at a very simple case, the probability of quiet shake-up. It's rather non-classical. If you kick a classical oscillator, do wait for some response. Quantum mechanical oscillator could be not excited during the shake-up. Right? So it just gets to the same ground state. What is this probability? Yeah, basically we have to put an M to 0 for all of this. And that's what we will find. It's exponent, and what we have is exponent just sum of average number of photons emitted to each mode. Fine, and now we are going to make something catastrophical before the break. Now we are going to understand what is this orthogonality catastrophe that has been put forward by Peter Anderson, really very, perhaps most the greatest condensed physicist of 20th century, very unconventional person with very strange ideas. Some of them appeared to be right, correct, and got him Nobel Prizes and glory. This orthogonality catastrophe, one of his first ideas of this kind. So, despite a low social skill, he was very influential scientist. Right. What did he notice? Okay, it's this P naught. It just, in fact, overlap between two vacua. Normally, if you talk about the finite quantum system, okay, there's still some overlap between two states. Right? So for any finite number of modes, this P naught is finite, small, but finite. But if you go to the limit of large number of modes, there can be two situations. Like if you go for a walk, you can either meet a dinosaur or don't meet a dinosaur. Probability 50-50, right? Same here. This integral can converge or it can diverge. If it diverges, if some or all modes diverges, that probability is 0. So after which means that the vacua do not have any overlap. Or in quantum terms, it means that these states are orthogonal. Turn something in the system, make the sum finite, they are not orthogonal. So that's what he regarded as a catastrophe. States which were not supposed to be orthogonal would become orthogonal. Yeah, if interaction with environment is sufficiently big. We can make sense out of that using our model, Spin-boson model. We can express these shifts for each mode in terms of the Cm and make sense of the Cm, and it becomes just integral for frequencies. And what comes here is imaginary part of the susceptibility. All right, and we want to assess the convergence of this integral. Usually these integrals do converge at high frequencies, there's no problem with this. We can always have some cutoff. The problem can arise at low frequency, at small omega. For instance, if imaginary part of chi is proportional to omega itself, what will happen to the integral? We will converge or diverge. Yeah, it will be low divergency. At low frequency, it will be d omega divided by omega. Right, so that's an example of orthogonality catastrophe. Good, I guess it's a convenient time for break. Let's have, or perhaps 80 minutes break. No, 7, sorry. Oh, I need to stop the video. Okay, good. Excellent, ladies and gentlemen, let me go on with the lecture. Orthogonality catastrophe. It's already quite a change, qualitative change, which one can achieve by changing, by choosing the environment. But it's only the beginning. For that, to go further, we would like to compute this probability to get energy in course of the shake-up, probability of energy change E at any E, not just at 0. Fine. It is a calculation you could do yourself at home, even without any supervision. As a result, it looks a bit involved, but it is again in terms of what you already know. Good, so what we want to compute, it's a starting point. We sum up, or we have a product of all possible modes, and within each mode, we sum up our integer number of photons in each mode. Good, we need to sum up this delta function, and this is less than handy. There is a common trick to deal with delta function. One can use the right knowledge of Fourier transformation. Right. It's one of the most powerful methods in mathematics and physics. It always comes handy here. So we present this delta function as integral over some variable t and exponent. Okay, we have now delta function. Now we can bring all these terms together to a convenient form. Good. And at this stage, we can sum up all this number of n in each mode. Although there are variable factorials, they all nicely sum up into exponents. Right. So we come here. We don't have n of m anymore, only averages of m. Still, it's a product over the modes. We want to go to the limit of discrete spectra. Then we can make it as follows. We can just put all that into exponent. We put all that into exponent. It's a function of time. We need to integrate this function of time. We have to make Fourier transform, but we can do it later. Now we can sum up over m. Presenting this sum as an integral over frequencies. This is similar to what I just done for orthogonality catastrophe. I expressed this in averages in terms of Cm and Cm squared, expressed in terms of the susceptibility. So here, right, let us look at the structure. We have P of E, it's a Fourier transform of some function of time. Okay? Here it's Fourier transform, here this function of time. This function of time is an exponent of other function of time. And this function of time, J, is an integral over frequency, so it's yet another Fourier transform. These Fourier transforms do not cancel each other because this function is the exponent. If it were a linear function, these two Fourier transforms would cancel. Okay, such a structure. Thus motivated, I rewrite it a little bit more comprehensive form. Look at this P of E, it involves processes with all possible numbers of photons, 1, 2, 3, 4, 5. I could introduce a probability to emit only one boson. I know that it's good if interaction is very small, if this parameter Q0 is small. Then I would emit only single photons, single bosons with this. Right. And the probability to emit would be proportional to dissipation, the imaginary part of susceptibility. Times this coupling constant Q0. Right. Okay, if I know that, I can get this formula for P of E, which is completely expressed in terms of P1 of kind of expresses probability of processes with any number of photons in terms of single photon emission probability. Right. Okay. Interesting integrals, but if you don't like integrals, I can. Okay, I still have to talk about something else. Right. Suppose we know this P of E, and it is a shake up. How to use this concept of shake up for a different, more physical situation. Now we have our qubit, and it is in an excited state. It tunnels between the states. When it tunnels, this influence would be considered as a shake-up. It tunnels between two levels separated by epsilon. Remember the qubit, that would be epsilon. So the transition probability, in fact, is proportional to probability for the environment to absorb this energy. Probability to get transition. So we can relate this P of E to the transition rate. The coefficient is here, yeah, one can derive it many ways. It's proportional to the square of tunneling amplitude as it should be. So in fact, it's implementation of Fermi-Golden rule for this rather complex. Right. What can I say? If you mostly emit by, if you mostly transit by emitting single photons here, then it's of course this. Good. That was about transition rate. I'd like to have yet another signature, yet another quantity to look at, which I can assess simply in this perturbation limit. And this is delocalization probability. This is delocalization probability, 1 minus probability to remain in the same. Oh, well. So for the qubits, without interaction, you have delocalization probability, which is d delta squared divided by epsilon squared. Where do I have it here? The slide. I guess here. I'd like to understand that in the presence of the environment. What kind of calculation should I do? I need to look at the correction to the ground state, which is the first order in delta. Right, those are coefficients of these corrections. And they are obtained by utilizing first order perturbation theory for wave functions. Okay, if I sum up of them, I got the same P of E function. The only point I need to integrate it. So here, how can I express the localization probability in terms of P of E? It becomes an integral. I could kind of write, I can make a foolproof check of this domain. If I don't have any friction, any dissipation, P of E just becomes delta function of energy at zero, right? So if I substitute delta function here, I reproduce the known formula for the localization probability. Good. So we will look basically in our investigation of a qubit in different environments. We will look at these two things as a transition rate and as a delocalization probability. Good. So now I'm working hard and I convert these integrals into pictures which you can easily accept. And it turns out that all possible P of E's corresponding to different environments can be separated in two classes. With an interesting and practical borderline between the classes. Right. These classes are separated by the notion of orthogonality catastrophe. As that dinosaur, which a regular method split, it either happens or not. If it happens, the probability to lose no energy is zero. And for most cases, at finite energies, it is exponentially suppressed. So it's very difficult to tunnel at all. At zero, it's absolutely impossible. At finite energy, it's possible, but it's exponentially difficult. Fine. P of E should be normalized to some average energy. So there are two examples of this function. So if it's zero at zero, it should have a peak somewhere at large energies, and the example is zero. What is the alternative? Alternative is to have finite probability to tunnel without disturbing the system. Elastic tunneling. Finite probability of elastic tunneling, that's what we call Kawai-Jacob. No orthogonality catastrophe. And well, in addition, we could also tunnel with dissipation. So there will be delta functional peak at zero, indicating possibility of elastic tunneling, and some tail when we emit basically one bosons. We still can lose energy, but yeah, most if the situation is like this, we mostly do emit only one boson, not two oscillating. All right, so these are two cases which, if you just look at the plots, are rather difficult to reconcile. What would be a plot which is in between? And the answer is indeed rather strange. It appears to be the borderline between these two classes is a family of functions which have power law dependence at small energies. Look, this red function and green functions, they have both power law behavior at low energy, but well, red functions perhaps -2, and green function, what will be your bet? Power law of green function square. Yeah, yes, reasonable. Right. So this presents a borderline between these two regions. So if you go to orthogonality regime, instead of power law, you would have exponential suppression. If you go to this regime, you would have finite peak, finite delta functional peak at zero energy. Good. Those are types of P of E. Right, and that brings us to this interesting person, Tony Leggett. He came up with this classification of the environments, and I personally would readily give him Nobel Prize for that. And he got one. But for some other stuff, which he did when he was kind of young and wild, it was something about liquid helium. It was also a contribution. I was asked to give kind of popular lecture about this Nobel Prize, or Prize lecture, and I did reading a conclusion of Royal Academy of Swedish Sciences or something like that. And I understood which paper does they mean that giving Nobel Prize to him. That paper, which has been published about 30 years ago, since the date, had 6 citations. You understand that it's not very much, kind of good scientific paper, even very involved, usually has like 10,000 citations. If it's famous. I really had to read it fast to understand why it was so. It was all okay. I mean, people read subsequent publications, review articles, they understood that Tony Leggett did so, but that short paper had kind of 5 paragraphs, and there was a great right discovery, the third paragraph, and blunt idiotic mistake in the fourth paragraph, which kind of compensated each other and gave 0 citations. But well, mistakes are forgotten, discoveries hopefully remain. So he got the Nobel Prize. But I guess it's better, it's the best what he did, this Tony, that classification of the environments which he gave. It is simple, but again, it takes a little bit an effort to understand all these power laws. It all depends how the function P1 of E, so one photon emission, behaves at low energies. That behavior can be characterized by a power which is S. Okay, we remember that one has to do quite a bit before getting from P1 of E to P of V. One has to integrate over energy, exponentiate, and get it back. And depending on this, one can have three cases corresponding to three cases which we discuss. And they have some fancy names which do not immediately ring the bell, but well, they have some mnemonic way to know. So let me make this name long. Sub, ohmic, super, ohmic, and ohmic. Sure, that are separated by the value of this exponent. Either it's smaller than -1, bigger than -1, or precisely -1. Right. And sub-ohmic is that orthogonal thing. Super ohmic is that elastic class. And ohmic is precisely the power borderline which we have considered in previous transparency. Fine. Why do we pay so much attention to this borderline? Also the name ohmic, it appears to be persistent. So, okay, everything is good except that all students have been kicked off. Fine. It's even easier. Classification of environment, sub-ohmic, super-ohmic, ohmic is important, practically important borderline. At the borderline, P1 of E is 1 over E. It's a coefficient coming here. And by a kind of simple magic, this coefficient appears to be an exponent, for eventual probability to lose energy. It's very strange. We kind of, in our physical education, we see power laws in plenties, but they usually have simple exponents 2, 3, 5. 5 is perhaps the fanciest you have ever seen. This law has continuous variable exponent, which you can tune with a hand. Changing alpha will change this exponent. Usually it's called anomalous exponents, right? Power law, which does have comprehensive power, it's good to call it anomalous. All right. That was the classification. Let me just go through physical consequences of that. If dissipation is sub-ohmic, there's no elastic tunneling involved. And it's good to say, it is, to make a long story short, it kills quantum mechanics completely. Why is it so? Our qubit just cannot tunnel without losing energy. It means that instead of a qubit, we have a classical memory cell. If you put a particle in one of the wells, it will stay there forever. Right. If you can supply a bit of temperature, if your energies, a little bit higher energies will become accessible, you will have exponentially suppressed tunneling between the wells, somewhat activated, very small. Right, one can see this as a dynamical barrier, energy-dependent barrier, which has precisely zero transparency, zero energy, but a bit finer transparency, exponentially small, at higher energies. Good. So our qubit is not a qubit anymore, it became a classical one. Right, let me do I have superomic? Let me jump to superomic first and then come to omic. Superomic, it is elastic tunneling, so here qubit survives. Owing to one electron processes, it still have some transition rates. If you put to excited state, it will decay to ground state. If there's temperature, it can jump from ground state to excited state. Right, that will happen with this exponent, with this probability, which also has exponential dependence, S. And let us see, let me compare this transition rate with the energy of the state. Transition rate, you can see it as a broadening of energy levels. So energy broadens by a value of gamma. So a quantum state is good in the limit of low energies if this gamma is much smaller than epsilon, right? Otherwise, the level would be too bright. So, depending on the exponent, one can distinguish two regimes in this superomic state. So, in both regimes, elastic tunneling is possible and dominates. But there is either bad or good quantum state at low energies. However, if one looks at delocalization probability, it looks at ground state of the qubit, it will always be finite. So this doesn't affect the fact that in the presence of elastic tunneling, qubit can be distributed between two bands. Okay, that was superomic. Let me look at the borderline at the ohmic case. All right. That ohmic anomalous power, that's what we have already seen. So P of E, which defines transition rate, is an exponential, a power law function with a variable exponent. Good, that's estimation of the rate. And again, we would try to determine whether it's small epsilon, so you have good or bad. And we understand that here we encounter a transition as a function of parameter alpha, which in practical situations is the resistance of the environment. Right, this transition has a name attached to it. It's called Schmidt transition. And in fact, it is a transition between something which looks like a qubit and has delocalized wave functions between two bells, and something which is, as described, a classical memory cell when the qubit just starts in one of the levels and don't dare to go anywhere. Right, so one can investigate it again, looking at transition rates and at delocalization probability, which is different on both sides of the transition. Good, that's called Schmidt transition. It's also discovery of like 40 years ago, 35 years ago. Okay, I told already about superomic. Let's see. Summary. That's a legged classification of environments. So let's summarize all that. What is the classifying parameter? Classifying parameter is an exponent in P of P1 of E, which is proportional to the imaginary part of dynamical susceptibility at low frequencies. So if you compute dynamical susceptibility, basically you can tell where you are in this diagram. What is S? Good. So there are two superomic cases. There are two ohmic cases on both sides of Schmidt transition, and there is subohmic guys. And the columns are kind of quantum signatures of a quantum state. Right, so the mass quantum regime is superomic with big exponents, and in this case we have delocalization between two bells. We have good state, and we also have resonance. One can make resonance between two qubit states by applying frequency. All right, then it increasingly become worse. In superomic, we lose good states at very low energies. The transition rate becomes too big, and the state is broadened, so one cannot make a qubit with very low energy spacing. It just would not work. Right, somewhere in the middle of ohmic regime, we lose localization. I should admit that the classification is not that linear, as it would be convenient for us to expect. Like in subohmic regime, we expect no signature of quantum states to be present. However, the signature in a good state is still present. It's kind of single state. You cannot transit between two states. That's why there is no resonance. But the state is good in the sense that it's distinguished from the excited states. Right, so that was summary of Leggett classification. The only thing which remains is to understand where we are in this classification, right? Of course, one can apply to very different physical situations, but let us apply to vacuum and electrons and atoms, something familiar. Before doing that, I need to make a small trick with a spin boson model. I would like to consider basically opposite limit of large delta and small epsilons. And what I would see there, the transitions, in this case, there will be still two states, strong tunneling. Those will be odd and even superpositions. They are induced by the environment. It's all the same. The only point, the energy associated with these transitions will be delta rather than epsilon. But all that classification of the environments will be the same also in this opposite limit. Okay, I do this in order to be able to describe transitions in atoms. Right, so let's concentrate on emission of light, which we have studied. We didn't have time much to talk about the atoms, but we can look at it. It was also homework about this. Emission of quanta. Emission of photons from excited states of the atoms. Okay, that was the expression of the rate which we have derived. Okay, there was speed of light, there was frequency, there was dipole matrix element over Go. What's important for me is that it contained the small dimensions parameter alpha, fine structure constant, which is in our world is small. Nobody knows precisely what is small. There's no kind of physical explanation or hypothesis, but it is a physical fact. This dimension is number is 10 to the minus 2. Fine. Let us understand what kind of environment we have. Okay, if we just try to combine it with the formula of the environment, okay, it is corresponds to transition rate omega to the 3. So it brings us to super ohmic with S equals 1. Good. And it might look that with atoms, and we are safe. We don't have to think any about fancy effects of the environment. We have states, well-defined atomic states, and undiscovered transitions. However, we've been talking about why this rate is so small. This rate is small because of dipole approximation. Atoms appear to be very small in comparison with the light wavelengths. That gave an additional small factor in this rate, proportional to frequency. Suppose we consider bigger dipoles. Suppose we make atoms bigger or let electrons to propagate at a bigger scale, not being confined by protons. Okay? Then we can have bigger dipoles like antennas, and maximum dipole is eventually, it's inversely proportional to frequency. It goes there. So if we take this fact into account, we appear to be in ohmic regime at borderline between orthogonality, catastrophe, and elastic. And that alpha finds structure constant is precisely exponent alpha in Leggett classification. So this anomaly is very small. But, well, this anomaly still persists. So, in principle, tunneling of electrons in our world also should be subject of orthogonality catastrophe. It's an effect which is hard to see, but in fact it is present. So, welcome to slightly anomalous world. Thank you for your attention. We'll see each other next. Okay, there will be a session day, so I guess in 2 weeks. I have to look at the schedule. Thank you.